Welcome to another exciting readings class. I see that it isn't snowing like crazy outside, so we had a slightly better turnout today, which is very nice. In our last exciting readings class, there were syllabi handed out to all the students, but because not all the students were here, I'm going to offer the syllabi again. Does everybody who needs a syllabi have a syllabi? Would you mind handing this out to me? Thank you. If you already have it, just spread it around. Whoever didn't get one should get one. Last time we talked about the syllabus. We went over it a little bit, but I'll just mention a couple of the highlights again. The first one is that homework counts in this class. It counts, thank you, it counts for 1/3 of your grade. And the midterm is also a homework, and it counts for 1/3 of your grade. So it's a take-home midterm. And the final is also a homework because it's also take-home, and it counts for 1/3 of your grade. And so at the end of this class, your final will be a thesis proposal, a proper engineering problem statement consisting of many cited and wonderful, hopefully, journal papers. You will be able to cast your problem with respect to other problems in the field. You will be able to describe the resources that you need. These include time, capital, and maybe even the efforts of others in order to be able to accomplish your research goals. And essentially, you are going to justify and motivate your research problem. You're going to describe any safety issues or ethical considerations that are needed in order to push the problem forward. You will also present the problem orally using perhaps PowerPoints, because engineers love PowerPoints, although that is not required. You will present your problem statement to the class. You will pitch the problem, and people will all understand your research proposal, and they'll be wanting to fund it with their own money so that you can go out into industry. The basic goal of the course is to develop both your oral and written communication skills, and also to be able to allow you to do what some would call intrapreneurship. Intrapreneurship means entrepreneurship inside the company, so that when you go to upper echelon management and you want to call the shots in terms of your research, they will give you the resources you need in order to push your research agenda forward. So you'll have these great ideas for the company, and the company management will say, well, why should we give you money? And you'll say, well, because you're going to have a return on your investment of 1,000-fold, and we're going to be able to make a difference in the world with this company. Come on in. So if you guys have some reason to suppose that you've got a good idea and you would like to pitch it, we here in the class would love to hear about your idea. And in fact, what I would do is I would go through some of the ideas that were listed here, because they're due. Ideas were all due here at 5 o'clock. And so I can certainly discuss some of the things that were written. And so let's review what the homework assignment was. It says here, you are supposed to have a title for your talk. List your name, the titles of your ideas, maybe describe the problems that you're interested in, your motivation. Why is this an important problem? Why should we care? The impact of the problem. Maybe we could talk a little bit about how you would approach your problem. What would you do to make the problem work? Maybe you need to write some computer program, or maybe you need to be able to build some hardware, or maybe there is some combination of the two things, depending upon where your interests lie. Some people had trouble finding an idea. Who here had trouble? Nobody? I don't believe you. Yes, you had a little trouble? It takes time. Of course it takes time. You don't wake up and say, today I will be brilliant. right? You have to come up with many ideas and decide which ones are good. What idea did you come up with?
I brainstormed a lot. I have on my hands again.
Should I go through your homework? Maybe we could just ask. You tell us, what is your idea?
Let me open it up. I have a couple different things. I was thinking about one of my main things was like implantable electrical devices, having to do with bioelectrical type engineering.
Like pacemakers?
Yeah, pacemakers, things to help with eyes, with seeing, vision, hearing. There's a lot going on with like wireless hearing aids, things like that, Bluetooth style hearing aids, and also like limbs maybe. Like when you lose an arm, they now have limbs that they can connect. Sort of your nerves control the limb, and your brain can send messages to this artificial arm that you have, things like that.
That sounds good. So
I have a lot of ideas.
you had a lot of ideas. Sounds like you gotta narrow it down a little bit. I have a thing here called the Grade Center, and we can see what needs grading. And it looks like there's many homeworks that have been submitted. Here's 23 out of 30. Remember, okay, it's 10 points per day late. So 10 points per day late means that you start with the possibility of 100, and then after 10 days, the most you can get is 0. So if at the end of the semester you say, "Oh, professor, here are all my homeworks," I could say, "I'm very sorry, but they don't count anymore." In fact, they get negative grade, because if it's minus 10 per day, then after 11 days it's minus 10, and after 20 days it's minus 20. And so we need a new grading system. We don't stop at F anymore. We go all the way through Z. And then if you get after Z, we start with other alphabets, like Greek letters. So it's possible to get an M. And when that cancels out the A's that you had for the prior several courses, because with this new grading system, you can do very badly. So I think it's very important that you hand in the homeworks on time. And I understand there are many creative and wonderful excuses. Industry does not care about your excuse. Industry does not care that there is traffic. Industry does not care that your car broke down. Industry does not care that you missed the bus. Industry wants you to show up for work on time. That is what professionals do. You are not fired for your skills. You're hired for your skills. You're fired for your behavior. Lateness at work is a reason to be fired. That is cause. So we are not late with our homework assignments, and we do not ask for extensions, and there's too many of us anyway, so I'm not going to give you extensions. You're already getting 10 points per day off, so if you lose 10 points on one assignment, it's no big deal. Just don't make a habit of it. So what I can see right now when I look at these things is I can see who submitted early, who submitted on time, and I can see right away who's waiting till the last minute to submit. And look, here is somebody who submitted at T minus 38 seconds. That's late. Minus 10. Now, how could you do this? 5 o'clock, and I can see who you are. Oh, okay. So as it turns out, I would accept it's not late. But I know, because of the timestamp, exactly when it comes in, and you can't say, "Oh, professor, I put it under your door and you weren't there," because this tells me I know. So you can't pull the fast one on me. So these sorts of things, it's very clear. And the first person to submit, it looks like Albert, who may be a distance learning student because he's not here. He has some ideas. Let's see if emergency medical bracelet. It sounds like something you could sell. And I know you can't see it. Oh, it says here it uses Apple iPhone. And talks to the phone and calls emergency medical training technicians. This is just like someone else who had the idea, the mushhead. Your mushhead idea. The mushhead idea, mushhead. There's two kinds of people, right? Electrical engineers, right? They're hardheads. Then they have the software engineers, they're soft heads, right? But then in between, the computer engineers do both the hardware and the software. They're the mush heads, right? So mush head ideas, which are good, they use both hardware and software, need to write some programs, and they need to build some hardware, both. And I think your idea involved perhaps using SMS and the cell phone network and microcontroller. This is very similar. You build a mobile app and communicates to the bracelet. Yeah, that's very good. I like it. Let's see. Here's another one. I'll just pick a couple more. Jeff Randolph, and it's a little small. I wish I could make it bigger. Let's see. How can I do these things? Voltage control resonate. Instantaneous change of radio frequency of a carrier as it moves from narrow to wideband and loses its frequency. It's very important to copy edit these things properly. This is one of those things I will grade you on. And if there is problems with your writing, it will be reflected in your grade. So this is one of those things you just have to really focus on. And if your writing isn't good, it will harm your grade. So you need to check your writing with others. Now, we have a writing center. I don't know if I mentioned this last week. Tech Writing Center is in the library, and they are there to help you. So if you want somebody to read your writing before you submit it, you can do that. And they will look at it, and they will help you with the copy editing. So it's much better for them to do it because they will not take points off, right? And they will help you. Is there somebody out there? Whereas if I do it, I take points off. So I'll write something in here, and then I'll do something or other, and your grade will not be as good as you like. Here's Mike's. We heard your idea. Oh, look at all this. There's like words on the page and everything. Some possible. The cat that killed the mouse. Surviving the power apocalypse. What?
I didn't know what kind of titles you wanted exactly, so I wasn't here last class. So I wanted them to be kind of catchy, but they basically reflect off of the ideas that I brainstormed.
So this is a biomedical device with some sort of electronic system.
Yeah.
Okay.
I started doing some research just to get some ideas, and this is the stuff that spoke to me.
That's very interesting. I love it. Biomedical devices are great. I love that stuff. Here's Anoop has an idea. Let's see this other idea. It's just very good. Pollution due to thermal power plants. So what does this do for me? Thermal power plant, coal is combusted. The help of oil, blah, 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 water remains is motivation. What is it you're trying to do? Dust particles. I guess it filters dust particles. It's not clear. Okay. We're going to have to learn how to do a proper problem statement. Oh, come on in. Okay. I have written 3 books. In my first 2 books, I was very disciplined. I had an outline. It was a formal, detailed outline. I followed the outline. I wrote every day, and I got the books done quickly. My second book, I decided maybe I don't need an outline because now I'm an expert. Big mistake. Big mistake. The outline, detailed, chapter by chapter, section by section, would have gotten the book done much faster. Instead, what I ended up with is, instead of a short book of 450 pages, I ended up with a book that was almost 1,000 pages long and took forever. And was not a particularly good book, not a particularly concise book. So, an outline is so important for a disciplined writer. It's so important for an undisciplined writer. Outlines are the structure about which we do our writing. When we put our head down and we focus on this section and then we pick it up and we go, what's next? It's very easy to tell because we've created a plan of action. And that plan of action is in our outline. And it tells us where we've been and it tells us where we're going. And if we decide to skip a section that we have to come back to and move ahead and write something else, it's okay because we can go back and we know just what to write in our outline. So it's one of those things where the outline is very important for us. And when it comes to this course, I have a very structured idea about how your outline should appear. A thesis outline is really very different from a paper outline. It's really very different from a book outline. It's different because it has to have a problem statement. An engineering problem statement is not the kind of problem statement that you would get from a chemistry class. It's not the kind of problem statement you would get from a sociology book. It's different, and it's not something you're born knowing how to do. It's something you have to learn. And so this is one of those things where you've already got some ideas, but you don't have a formal engineering problem statement. And so that's one of the reasons why some of these ideas are a little hard to read. Like someone will say, oh, I've got coal dust. Okay, that's a problem, but it's not a proper engineering problem statement. And so what I'd like to do is introduce you to that idea, that concept. So, first I'll talk a little bit about an outline. How many people here have written an outline before? A couple. One. No one else has ever written an outline? Really? Don't they? You guys do writing, right? And undergraduates, do they not require some writing? They may not. Did anybody take a college-level English class? No. You just knew it already. Okay. So what I'd like to do with the outline is describe for you some of the things I expect. In the first introductory section in the outline, I would like the proper engineering problem statement. The second major chapter in the outline I would like to have is a historical review. These two areas, these two chapters, will be the primary outcome of your course, of this course. So when you're done, you're going to have Chapter 1 for your thesis and Chapter 2. You're going to have a thesis proposal with an outline that has a problem statement in your first chapter, your introduction, and it's going to have a historic review in your second chapter. And so inside of that first chapter where the problem statement is, you're going to have your approach, your motivation, ethics, safety concerns, and a proper engineering problem statement. So in the world of engineering problem statements, usually what you want to do is start with a discussion about your assumptions. If you get into a debate with anybody about any topic, the first thing that will simplify the discussion and make it productive is if you state your assumptions. Okay? So let's assume, for example, that we can represent natural language with logic. Now, I'll tell you right away, that is a bad assumption. Okay? But let's make the assumption. If you assume that that is true, that logic is not an impoverished representation of natural language, then you can make certain statements that are analytic and correct. For example, a bachelor is an unmarried male. We know that's an analytic statement because an unmarried male is also a bachelor. So it's true both forwards and backwards. And logically, it makes perfect sense. But if I said to you, God is love, and love is blind, and Ray Charles is blind, does it mean that Ray Charles is God? No. So what I have done is I've created an example of why logic is an impoverished representation of natural language. there are certain things that don't represent very well in terms of analytic closed form statements in logic. So now I've got this idea that assumptions have to be stated right up front. And with problem statements in engineering, I want to make sure you know the assumptions. Make sure you know the constraints on the problem. Because in life, what happens is the problem remains the same and only the constraints change. And so what you do is you start off by saying, I want to study some area where we can transmit data from here to there. The assumption is we use a phone line. Okay, that assumption is surely going to be relaxed over time because eventually you're going to stop using a phone line and you'll be using fiber optics, or you'll be using a coax cable, or you'll be using RF, like Wi-Fi. So as you change the assumptions, the problem may have it's the same problem. I want to get data from here to over there. But I've changed the media over which the data traverses, and now the error rate, the bandwidth, the signal-to-noise ratio, all these things have changed. And that changes the problem in a material way because the assumptions changed. So we start with the given, the assumptions. And so that's so important to the discussion, and it's so important to making sure that debate is productive. So when you start with a problem statement, I say, look, given some condition. Now, you know, let's think about it a minute. Let's assume for the moment that I want to transmit data using wireless sensors. Wireless sensors that don't use batteries, that do parasitic energy harvesting. Let's assume it's in a helicopter. Well, one thing I know about helicopters is they vibrate a lot. So now I have all this random energy available to me from vibration. Harvesting vibration in a helicopter is not particularly difficult because helicopters vibrate a lot. So all I have to do is put in vibration sensors that can essentially harvest the vibration energy because of that assumption. Now, take the same sensors and put them in a car. They don't work at all because I don't have that vibration anymore. That's a totally different problem. Maybe I can work off of thermal engine heat. Maybe I can work off of solar or RF energy harvesting, but not vibration because I don't have enough. So, this is advancing without me. So given some condition, whatever that may be, subject to a whole bunch of constraints, whatever they may be, we want to find a solution. And you could state it just that way. We are given this situation, we have these constraints, and the constraints can be constraints on your budget, constraints on your bandwidth, constraints on whatever it is you're using for your problem. I don't know. And so now I've got this, I'll call it folk theorem about a proper engineering problem statement. A good problem statement is a necessary but insufficient condition for finding a good solution. If you didn't state the problem well, the chance of your being able to solve the problem is diminished. And so I would say that being able to formulate a correct, formal engineering problem statement is one of those things you were not born knowing how to do, but which you must learn. You must learn. So that's one of the things that you're going to be able to lay claim to when this course is done. So if you say, geez, I've got this problem, and the problem is, oh, they don't have clean water in Bolivia. Well, that's certainly a problem. But it's not a proper engineering problem statement. So you might say, given a situation where there's very high humidity and where no clean water is available, subject to the constraint that villages are impoverished and people are dying from tetanus and typhoid and all these things that happen from unclean water, how can we come up? We want to find a way to produce clean water cheaply so that people can afford it. And maybe what we can do is make use of the fact that there is good humidity in the air, and we can condense against these certain surfaces and drip clean water into an area that people can drink and find potable. That sounds like you're getting close to a good engineering problem statement. So lots of interesting ways you can motivate that kind of problem, right? Think of the people who die from unclean water. think of the people who are very interested in making sure that the clean water is significantly available. You might say, but wait a minute, this doesn't make me any money because they don't have any money and I'm building something that has to be given away. And you could say, well, there's ways to fund this stuff. We call it social entrepreneurship. Right? Social entrepreneurship means you raise money for a good cause. So, one could say, but wait, here's a professor who's talking to me about these things and he's working at a non-profit university. Most universities are non-profit universities. This is one of them. Well, non-profit organizations need money because employees of the non-profit organizations, like me, are very fond of getting paid. We like that. In fact, if you stop paying us, we probably would stop going to work. And you wouldn't have this wonderful lecture. So, as a result, I would say social entrepreneurship, even for nonprofits, have to be very focused on things like a budget, things like raising money and top-line sales. If I think about the difference between science and engineering, what do I think about? Why is science different from engineering? You guys are engineers, right? You're in an engineering program. You probably all have engineering undergraduate degrees, most if not all of you. And you chose engineering. So you must have had this idea in your head. Why is engineering different from science? You're going to have to tell me. Yes, sir.
One thing, when you do a scientific paper, you have a hypothesis, not a problem statement. So it's
That's very good. The scientific method says you create a hypothesis and then you design a test in order to be able to check the hypothesis. And if the test validates the hypothesis, then you have collected data. But if the test invalidates the hypothesis, then you've made a discovery. So this is very interesting because science is really about discovery, right? An astronomer uses a telescope to discover things about the heavens, right? This is very interesting stuff. They're discovering new planets where maybe there is life. But engineers build the telescope, right? The engineers, the optical engineers, sit down and find new ways to construct things that never existed before. New instruments that extend our senses. Maybe there is a compelling argument that the scientist discovers what is, but the engineer invents what isn't. So we, as engineers, we're designing new things, creating new technologies, things that make a difference in our society, right? Scientists didn't discover the cell phone, right? I can go for an exploration. I've discovered the cell phone. Oh, look, what does it do? Oh, it opened. This had to be created by an engineer. It was devised as an invention. Now, maybe you could say, if it wasn't for the scientist, you wouldn't have the cell phone because somebody discovered electromagnetic energy propagation. Somebody discovered radio waves. Somebody discovered electricity. And I'd say, absolutely, science is terribly important. But the engineers have a different skill set. Engineers design. And scientists are not skilled in the area of design. Yes, a physicist knows all about forces. But a physicist does not design the bridge you drive your car over. Because if the physicist does that, either they're a civil engineer or you're going to fall into the river with your car. Right? So as it happens, being skilled in the area of design is a very different thing than being able to do discovery. So when you do your motivation and you say, geez, I'd like to be able to make use of some scientific principle, I'm probably going to do something that's going to make a device that's impactful to society. Now, a lot of times engineers, like me, create papers, patents, and prototypes and never, ever bring a product to market. If you don't bring a product to market, your ability to have impact may be quite limited. So part of what you are doing may be to create an early prototype that could be brought to market, that could even bring in some sort of funding so that you can say, aha, I can start a business. Or look at this, I can spin off this device and sell a license and bring in royalties. So this is what people will call engineering entrepreneurship. That's when you take innovation and target commercialization. That's when you can really make a societal impact that makes a difference, that changes the world. But there's something else about your problem statement. It should be able to contribute to the body of knowledge that exists already. And this is part of the historical review. The historical review is going to make sure that you can see what has been done and how what you're doing is just like what's been done with a difference. And the difference will be something that you can describe. So when you talk about motivation for a problem, I'd like to know who's going to care about my solution. Why should I care? I've got a new widget and it lets me do camera tracking. Does anybody care about camera tracking? Who will buy it? Who cares about this? If the only people who care about it are professors who do distance learning, will I be able to sell it? Maybe not. And if I do decide that the market is very small, will they pay the big price that I need to charge in order to be able to bring it to market? If I don't have the volume, I've got to make up a larger profit margin in order to be able to make it in smaller quantity. So these are things that we would like to be able to think about. Who will use my solution? Who will care about my device? I like these ideas about thinking in terms of your research as having impact. This is so important. A lot of time people will labor on merely interesting ideas that have very little impact, and sometimes they can labor for years on these things. And that's terrible, because what happens is after these years go by, you cannot get them back. They're gone. And if you have nothing to show for it in terms of what you've been able to contribute to society, then you'll be forgotten when you are dead and rotten. So you have to do the things that are worth reading about, or do the things that are worth writing about. So I'm thinking that this is one of those things. Motivation will allow us to say, yes, this is an important problem. I need to know something or other about what people will do with your solution. Will there be other problems that are related? Will I be able to build on the problem? You know, if you told me, well, I've got a good problem where I can automatically park a car, but it has applications for docking in general. And maybe what I can do is I could say, look, this impacts autonomous land vehicles, or this impacts the ability to take the space shuttle and rendezvous with a space station. You know, these trajectories that come in for parking the car have implications for other kinds of robots and for other applications. And so I could say, you know, there are these things that look like I'm really targeting just one specific application, but there are these other applications, broader concepts. I had one problem I solved. It had to do with diffraction range finding, very general. And then I said, you know, here's one sort of, I'll call it platform technology. Now we can apply it to these different areas. Here's a biomedical device. Here's a thing that scans objects on a turntable. Right? It could be used in both areas. So lots of potential applications. Then comes this other subsection in your outline, the approach that you plan to take. You may say, geez, you know, I need to be able to create some experiments, to do some prototyping. I've got to be able to build some hardware and write some software. I'm not sure what the approach will be that you will take. And you'll have to think about that, because solving a problem always requires some methodology. Later, we'll talk a little bit about validation. Validating a hypothesis means coming up with experimental results. So we have a project I'm working on with some seniors and some graduate students now. It has to do with fractal antennas. We made certain predictions, and we fabricated our fractal antennas. The predictions were the antennas would be able to transfer power from one place to another at 2.4 gigahertz. Well, validation means taking the antennas and attaching them to an oscillator that sweeps from one frequency to another in increments in order to see where the antennas peak in their power transfer. So I've got the simulations, I've got the theory behind why this should work, but I don't really know until I do an experiment. That requires me to actually do a setup, take a measurement, and then validate the hypothesis. And if the hypothesis is wrong because I forgot to take into account the dielectric properties of my printed circuit board, well, that's one of those little things that you didn't think of, that didn't show up in the simulation, that can't show up in the modeling, that really have to be taken into account for a real antenna. That's such a typical problem when you go to a nice practical application. That's why we validate these things. And then you say to yourself, but I can't measure 2.4 gigahertz because the highest frequency oscilloscope that I have available only goes to 100 megahertz. Well, guess what? We ended up buying a $12,900 oscilloscope so that we could measure out to 10 gigahertz and try different antennas in these microwave ranges. That was so important, but it was part of a resource that needed to be written about and justified to upper management before we could be allowed to spend that kind of money. It was very expensive. But we needed at least one good oscope here on campus in order to be able to do those measurements. It's very important that you all use this course's title as the driving, motivating factor for what it is you do. It's called Readings for a reason. And that means you're going to end up doing a lot of reading in this course. By the time you're done, I would say you'll have in excess of 40 papers that'll be cited in your thesis proposals. These papers are probably going to be papers that are good, and some will not be so good. But all of them should be relevant to your work. All of them should be peer-reviewed papers. All of them, if not most, will be journal papers that you've ordered from the library. And ordering journal papers from the library is something that you will do every week and something that we will document. So you'll have a homework assignment that will include something like an outline, and then at the end it'll say, and 10 journal papers that you ordered from the library. And then there'll be another thing that'll say, engineering problem statement and another 10 journal papers that you ordered from the library. And maybe summaries in 2 weeks from the first 10 journal papers that you ordered from the library. So you'll be doing readings and writings, summarizing all the papers that you've written about. And you will become experts in these areas. So you may have written about some problem that maybe you didn't care about very much. You may have to revisit the problem. Because if you don't like your problem now, you're going to hate it by the time this course is done. So you might as well pick a problem you like. That's the way it is with a thesis. Thesis topics are topics that sometimes you can get sick of. And then you know you don't really want to do a thesis on it. You should really like your thesis. I can't tell you how important that is. If you don't like your thesis, you better find a thesis you like. So find something you're interested in. And this is part of a search. This is like a soul-searching thing. It's like finding out who you are or who you want to be when you grow up. It's a tough problem. So finding the right problem is an important and actually is the most important problem. Because if you're on the wrong problem, you can forget the whole rest of it. Is there a question? It's out there. There are these things which we call societal implications in the thesis topic outline. I like to put in something about ethics. Everyone here has a code of ethics. It could be, I think, in this room, probably the IEEE code of ethics. So we have an IEEE code of ethics. I'm a senior member of the IEEE. The code of ethics in general is laid out for everybody to see, and will describe the ethics and how we can make ethical choices. Ethics from a professional point of view are really little more than rules of behavior. It's not morality. Morality is like right and wrong. Ethics are different. And you know it's not morality because in our legal profession we have lawyers who are required to give good defenses even to people who they know are guilty. Right? And so what they'll say is, well, my client is an axe murderer and child molester, and they're going to do it again and again and again, but I have to defend them and try and get them off because they're entitled to a good defense. Now, that may offend your sense of morality, but it is ethical from a legal standpoint. So this sense of ethics has little or nothing to do with the sense of morality. So we'll try and learn how we can judge the ethics. Safety. That's a tough one. Everyone is going to have issues regarding safety in their device. If you have a biomedical device, Mike, and it's going to go in your body or on the body, there are safety implications there. Electrical stuff in the body is subjected to regulation, right? FDA regulations, efficacy studies, clinical trials, preliminary medical applications, PMA applications that go in front of the FDA, all are part of the safety considerations. So these are important things. If you told me I've got an artificial pancreas, I had a guy who was working on his PhD thesis in the school where I was at, and he was working on exactly that, an artificial pancreas. It used linear systems for control, and it also had fuzzy logic for when things got out of control. And it was trying to regulate the insulin level inside of somebody's blood. And if you do that wrong, you can put them into insulin shock and you can kill them fast. And if you do it right, you can make it so that they can extend their life over a long period of time, because a lot of times people who are dependent upon insulin don't regulate their sugar properly. So we've got all kinds of interesting safety considerations for that thesis. So your outline is now done with Chapter 1. That was your first chapter. You can sort of see why the outline is so structured. If everybody has the same general outline, it doesn't mean you have the same problem. Quite the opposite. You all have different problems, but the outline is going to give you a structure upon which we can look at those things that you need to write, so you know exactly what is expected of you. I'm thinking you might be tempted to list a bunch of papers that you don't write about. Avoid that temptation. Only list the papers that you write about. Every paper should contribute something to what you have written. Every paper should be cited. I want to know why the paper is there. How did this paper relate to my contribution? What did this paper do to contribute to the field? Why is the paper important? What did the paper claim? And do you think this paper is correct? If they made these claims and you don't think it's correct, that's important. Sometimes people write these papers and they publish data that doesn't look right. Maybe it's good to be skeptical. Maybe it's good to say, I saw this and I tried it and I couldn't get it to work at all. Repeating the experiment is the most elementary of laboratory behavior. Someone says, I've discovered cold fusion. You take 3 tea bags and you put it in a tea thingy and blammo, infinite energy. You say, oh, that's a good invention, if it works. But can I repeat the experiment? And they say, well, here, let me try. Oh, I spilled the tea all over myself. Oh, this is terrible. Well, but take my word for it, it works. Oh, you have to repeat the experiment. So I say, and there was a big cold fusion thing going around. Do you remember this? Everybody said they had discovered the secret to cold fusion. Wow, isn't that terrific? But in fact, they didn't. And no one could repeat the experiment. And so this elementary laboratory behavior, repeat the experiment, couldn't be done. I think somebody else did something like this, discovering a faster-than-light system for communicating from one point to another, and then they said that didn't work either because they'd flubbed the experiment. They couldn't repeat the experiment. So now comes to this issue about validation. How will you validate your hypothesis? After you've done your thesis, you will have been able to look back and say, here are these experimental results. I will set this up, and I expect to be able to reproduce these results. I'll make some model, and I'll be able to say this model is good because I set up a real thing and did some measurements, and it validated the model. The predictions I made were correct. So after you've got the validation set up, you've designed your experiments, you described what it is you expect for results. My thinking on this is, what's your timetable? Is this thesis doable? Can you finish it in the time allotted? Well, I'm going to write a new program every week and it's always going to work. Yeah, that doesn't sound good. You better give yourself some time for debugging. It's going to take time to develop code. So these are the kinds of things that you want to think about in terms of your timeline. Some people will do this formally. They'll use a Gantt chart, which, I don't care if you do that. They'll use Microsoft Project. I don't care if you do that. You may use Excel. I think that's good enough. You may just list out what you do and how long it takes. That's probably good enough. There are all kinds of ways you can do milestones. How many pages will your thesis be? When you get to the midterm, it's got to be at least 6 pages, I should think. If you're going to do 22 and a half papers by then, because there's 45 papers total for the semester, and you're going to write a little bit for each one, a couple or 3 paragraphs, it seems to me that you're going to take some substantial amount of wordage in order to be able to do it justice. It doesn't matter to me if it's too long or even too short, but you're going to have to do something to show that you've done the work, that you actually read the papers. What about copying the papers? Can I just copy them? No. That will hurt you. If you just take the papers and quote them lock, stock, and barrel without rephrasing the papers, it will be reflected in your grade. So you need to rewrite what's in the papers in your own words. Summarize the whole thing in a couple of paragraphs and that's it. Move on. I don't want to see you just take whole chunks of something you found on the web and slap it in your thesis proposal. That's bad. Okay, really bad. So don't do that. TOC stands for Table of Contents. PS stands for Problem Statement. This is one of those things where each one of the homework assignments we give you will help you toward this midterm. Once you get to the midterm, you'll be gluing together a lot of these homework assignments that you've done. So the homework assignments all contribute to the midterm, and the homework assignments and the midterm all contribute to the final. And in between there'll be presentations and more interesting and wonderful chats like this one. When you go to your literature, you will have to organize the literature. And the big question about how you organize literature is a question of how you represent and organize knowledge. Knowledge is an interesting thing to try and represent. A good knowledge representation is the central heart and soul of any artificial intelligence program. Representing knowledge is one of the things that a good research paper should be able to do, because it takes the areas that you've visited and puts them in a nice, clean organizational structure. I like to think of it as a taxonomy. A taxonomy is a directed acyclic graph. An acyclic graph is one where the leaves don't connect to one another. A directed graph is one where every arc has a direction. So when I think about the taxonomy for control, I think, me personally, because I'm a control guy, I think, well, there's two kinds of control: classic control and modern control. Right? Modern control, neural network control, fuzzy control, maybe high-end artificial intelligence-y type control with expert systems. Meanwhile, classic control, linear systems, maybe we'll call it Ruth Hurwicz's criteria, stability analysis, basic control theory. That's classic control. And so then there's, these two different areas. When I say, like, my thesis is on fuzzy logic, I can say, well, it's really in the area of modern control. And I can ignore classic control and start to review papers in modern control. And now I can say, aha, well, there's fuzzy control and neural network control, and my thesis is fuzzy control, so I'm going to ignore the neural network control papers and just focus on fuzzy. So in some sense, that taxonomy helps me break the literature down into its subparts. And in classic control, I could say, there are heuristics and stability analysis and transform techniques, all these different areas of classic control. In modern control, there's intelligent control and optimization theory, two kinds of things. And in intelligent control, I may have fuzzy, neural, and hierarchic control. And I could say, well, I'm going to ignore hierarchic and neural, and I'll just focus on fuzzy. And now I want a whole bunch of papers on fuzzy, but I can say there's a whole area in here I didn't look at. And so that's important for me. Now, I thought it might make sense to take a little bit of a break. So what I'm going to do is I'm going to stop for now, and then we'll come back in about 5 minutes. So let's take a break.